Hello viewers, in today's session we are going to discuss some important problems related to parametric differentiation, right? And we have already discussed the concept of parametric differentiation in our earlier videos. So here we'll solve some important problems. So the first problem is we are given two functions, that is x is equal to cos inverse of 1 over square root of 1 plus t square, and y is equal to sine inverse t over square root of 1 plus t square, where t is a parameter and here t belongs to the set of real numbers, right? So here we are given that x is a function of t and y is also a function of t, and we have to find dy over dx, that is the derivative of y with respect to x, and the second derivative of y with respect to x, right? So here t is a parameter and we have a function y is equal to f of x, where x depends on t and y also depends on t, and further y is a function of x. So let us see how we can find out dy over dx and the second derivative of y with respect to x. So now to get the value of dy over dx, what we do, we first find dx over dt and then dy over dt. So first we find the derivative of x with respect to t, then the derivative of y with respect to t, and then we find dy over dx by dividing dy over dt by dx over dt. So the first objective is to get the derivative of x and y with respect to t. So here x is equal to cos inverse 1 over square root of 1 plus t square. So we have to find dx over dt. Now see here we have a function of cosine inverse. So let us first simplify x and y by method of substitution or by introducing another parameter. So to simplify x and y, the most appropriate substitution is t is equal to tangent of say theta, right? So when we take t is equal to tangent theta, then we can simplify x and y, and then we can easily find out the derivative of x and y with respect to t. So when t is tan theta, then x is equal to cos inverse 1 over square root of 1 plus tan square theta. Now from trigonometry, we know that 1 plus tan square theta is equal to secant square theta. So 1 plus tan square theta is secant square theta. So this is cos inverse, and here this square root get cancelled with this 2 and we are left with secant theta. So now we have cos inverse, and 1 over secant theta is cos theta, and from inverse trigonometric functions we have cos inverse and cos, it get cancelled and we are left with theta, provided that the principal value branch of cos inverse, it belongs to the interval that is 0 to pi. So we have x is equal to theta, where theta is given by tan inverse of t. So now we have x is equal to tan inverse t. Now we can find out dx over dt by differentiating tan inverse t with respect to t. So the derivative of tan inverse t is 1 over 1 plus t square. So this is the standard result. So dx over dt is equal to 1 over 1 plus t square. So now similarly, we can simplify y. So y is sine inverse t over square root of 1 plus t square. So sine inverse is equal, this is tan theta for t, and here we have 1 plus tan square theta. So this is sine inverse, and we have tan theta, and square root of 1 plus tan square theta is equal to secant theta, as we have done in this case. So we have sine inverse, tan theta is sine theta over cos theta, and 1 over secant theta is cos theta. So cos theta and cos theta get cancelled. We have y is equal to sine inverse sine theta. Now again, from inverse trigonometric function, sine inverse and sine, it get cancelled, and we are left with theta. And provided the principal value branch of sine inverse is from minus pi by 2 to pi by 2, right? Okay. So here we have y is equal to theta, and theta is equal to tan inverse of t. Now dy over dt is equal to the derivative of tan inverse t, that is 1 over 1 plus t square, right? So we have obtained dx over dt as 1 over 1 plus t square, and dy over dt as 1 over 1 plus t square. So now dy over dx is equal to dy over dt divided by dx over dt. So dy over dt is 1 over 1 plus t square, and dx over dt is also 1 over 1 plus t square. So 1 over 1 plus t square and 1 over 1 plus t square get cancelled, and we are left with 1, right? So dy over dx is equal to 1, and we can see that the derivative of y with respect to x is a constant. So when we differentiate dy over dx to get the second derivative, that is d2y over dx2, then we have d by dx of 1, and the derivative of a constant is 0, right? So the second derivative, that is d2y over dx2, is equal to 0. So now consider this important problem. So here we are given a curve y is equal to f of x, which is defined by these two equations connecting x and t, and y and t. So here x is given as a function of t, y is also given as a function of t. So x is equal to 2t minus t square, and y is equal to 3t minus t cube. And we have to find dy over dx when t is equal to minus 2, and the second derivative of y with respect to x, that is d2y over dx2 at t is equal to minus 2, right? So let us first differentiate x with respect to t. So dx over dt is equal to d by dt of 2t minus t square. Now the derivative of t is 1, and the derivative of t square is 2t. So we have 2 minus 2t, that is 2, taking 2 as common, we have 1 minus t. Now similarly dy over dt is equal to d by dt of 3t minus t cube. So here again the derivative of t with respect to t is 1, and the derivative of t cube is 3t square, right? So here we have used this result, that is the power rule, that is the derivative of t raised to n with respect to t is n times t raised to n minus 1. So here we have 3 minus 3t square, and taking 3 common, we have 1 minus t square. So now first we'll find the dy over dx. So dy over dx is dy over dt divided by dx over dt. Now see, dy over dt is 3 times 1 minus t square, and dx over dt is 2 times 1 minus t. Now here we have 1 minus t square, and it can be factorized as 1 minus t and 1 plus t by making use of the identity a square minus b square, that is a minus b, a plus b, and here we have 2 times 1 minus t. Now this common factor get cancelled, so we are left with dy over dx is equal to 3 times 1 plus t over 2, right? And we have to find the derivative at t is equal to minus 2. So dy over dx at t is equal to minus 2 is given by 3 times 1 minus 2 by taking t is equal to minus 2, and here we have 3 by 2 times minus 1, that is minus 3 by 2, right? So the slope of the tangent to this curve y is equal to f of x at this point t is equal to minus 2 is given by minus 3 over 2. Now let us find out the second derivative of y with respect to x. So now the second derivative, that is d2y over dx2, is given by d by dx of dy over dx. So now let us substitute dy over dx as this quantity. So we have d by dx of 3 by 2, and here we have 1 plus t. Right now 3 by 2 is a constant, so we have 3 by 2, then we have d by dx of 1 plus t, right? So we have 3 by 2. Now see, the derivative of 1 with respect to x is 0, being a constant. So we have simply here dt over dx. So the second derivative, that is d2y over dx2, is equal to 3 by 2 times dt over dx. So now from this expression, we see that dx over dt is equal to 2 times 1 minus t. So if we take the reciprocal, then we have dt over dx as 1 over 2 times 1 minus t. So we can now substitute dt over dx equal to 1 over 2 times 1 minus t over here. So we have 3 by 2 times 1 over 2 and 1 minus t. So this is 3 by 4, and here we have 1 minus t. So the second derivative, that is d2y over dx2, is 3 over 4 times 1 minus t, right? And we have to find the second derivative at t is equal to minus 2. So substituting t is equal to minus 2 in this expression, we have 3 over 4, and here we have 1 minus minus 2, right? So this is 3 over 4, and here we have 1 plus 2 minus minus plus, and here we have 3 over 4 times 1 plus 2 is 3. So 3 and 3 get cancelled, so we are left with 1 over 4. So the second derivative at t is equal to minus 2 is equal to 1 over 4.